Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So basically, we're going to start today by, obviously, the first thing we need to do when we're making a decision on what sort of power divider we want to get is we have to see what kind of power divider do we need. So basically, we'll go through an overview of what sort of parameters drive the needs of a system, and then we will move into a discussion as to what are the various choices that we have for the various power divider configurations and construction techniques. What are the pluses and minuses of some of those? We'll then go through some decision examples, and then wrap it up with a summary and a quick review of some of TRM's differentiators.
Well, thank you. And to get started, I assume we begin by assessing total system requirements.
Absolutely. Everything comes down to really what supports the overall system mission, and what does the system need to do in order to fulfill its use. Every system has an important use that needs to get accomplished, and all of the individual pieces, work towards delivering those sorts of parameters. So the first thing that you need to do is, well, what frequency is the power divider need to operate over? How much available size? What sort of packaging requirements? What sort of environment will the divider need? As well as power. These are all things that really affect the overall packaging that the power divider will require. And these are actually really critical items to understand up front as far as to what frequency it's going to operate up, and then what sort of packaging is required to fit in the system. Things I have listed here are sort of second order parameters, and a lot of electrical engineers may disagree with this, but these are the electrical parameters. Things like VSWR, insertion loss, and isolation are electrical parameters that are very important, although if it doesn't fit and you can't mount it, it doesn't really matter what the VSWR parameters are, because it won't work in the system. So these are the sorts of things that you need to understand, and really you can't ignore any of these going into a decision matrix, and if you're going to make an intelligent decision as to what sort of power divider configuration that you want to get.
Okay, so what comes next?
So the first thing we start looking at here is the frequency. The frequency of operation will determine, to a large extent, or limit the sort of construction techniques that we're going to work with. If, for example, if the frequency range is in the kilohertz region or 2 or 3 megahertz, that's going to eliminate strip line or any sort of distributed elements, just because of the physical size of the part. These things are all based on quarter wavelengths of lines, and at that frequency, a quarter wave is many meters long. So the packaging for those sorts of devices just becomes very impractical. Conversely, if we're working something up in Ka band, the parasitics coming off of a wire-wound transformer will make the circuit virtually inoperable. So therefore, you have to go to a distributed sort of network. The graphic on the screen here shows TRM's technology matrix, and you can see the various lines on there showing the split over where these technologies are typically operating over. You will notice that through the UHF through L band up into the low part of S band, there's a wide variety of technologies that are available, and they all function at various levels. So it's in that band, you have many choices. Go higher than that, your choices become more limited, and go lower than that, and your choices become more limited. But really, this is the first sort of decision maker that you get is with the frequency of operation that does dictate to some degree or limit to some degree your choices in how you're going to manufacture the part.
Okay, and a few minutes ago, I heard you say that everything had to fit, or a lot of these other things don't matter. So I'm guessing that size requirements or restrictions might be highly important. Could you clarify?
Sure. So the next thing that's really really important is how much room do you have in the system. There are, and the bottom line here is if it doesn't fit in the system, it's not going to work. So you know the packaging has to be able to work within the system. If the real estate available is only for an SMD surface mount type device and very, very small, then clearly a large distributed connectorized part will not work in the system. We have to go through there and see really, is this part of a system where it's going to be mounted out by an antenna array, in which case you want a coaxial sort device, or is it something that's going to be inside of an up or down converter, in which case you may want to have something the surface mount. Things that affect size are the technology approach. A lot of the low frequency ferrite type devices can be quite small. They also can be quite large, and that's really dependent on the power handling capability or what is required of the system from a power handling standpoint. We make some very small low frequency components that will fit basically and that are SMD. We also make some that cover the same frequency range that are 19-inch racks. The difference there being power. One will handle a half a watt, and the other one will handle 10 kilowatts. So there's a tremendous size difference depending on the power handling capability of some of these devices. Also, things that affect size are bandwidth. A very broadband, high frequency strip line part using distributed elements will be much larger than a narrowband strip line part, simply because of the number of sections that are involved. Things also that affect that are overall electrical performance. Broadband parts tend to have more degraded electrical performances just based on additional line length. So things like insertion loss and isolation tend to be not quite as good for a broadband part as what you get for a narrowband part. So these are all things that we have to be cognizant of as we're making the decision as far as to what sort of device that we're going to end up with.
Yeah, makes sense. Can you tell us a little bit more about how environmental considerations fit in?
Sure, and this is the next piece of the puzzle here. All of the devices within the system need to perform over some environment. Now, some environments are very benign, and for those sorts of environments, you can be much more lax as far as to what you do for your packaging. But really, the environment does determine, to a large degree, what sort of packaging is required. Does it need to be sealed? Does it need to tolerate salt? What sort of mechanical mounting considerations are required for the system? And how are we going to connect this electrically? Will it be an SMD type device? Will it have connectors on it? Is it a very high power device, in which case does it need very large connectors? Does it have a high altitude sort of environment, in which case you have to start worrying about critical pressure, or in space applications where you have to worry about multi-paction effects due to those sorts of breakdown sort of considerations going in very low pressure environments. So in those environments, not only does it affect, the sealing or the venting of these parts, but also it affects the way that the connector launches are done. And sometimes it affects actually the connector selection. If we're coming in with a high power, high altitude part, for example, something that may work at sea level with an SMA connector may very well break down at high altitudes, in which case maybe you have to go up to a TNC connector as opposed to an SMA to mitigate some of those issues. So those are all things that need to be thought of as we're going through the various design choices. Something else also is that not all technologies are appropriate for all environments. And that has a lot to do with the mechanics of how a component's going to react to its environment. A good example of that is that, for example, a strip line or microstrip sort of construction will be much more robust than a lumped element sort of construction for a high shock sort of environment or a high vibration environment because of the mechanics involved. And then again, if you're going on a spacecraft, that adds a whole other level of breakdown issues that need to be addressed.
How about power considerations?
Power is the next really big thing that we need to look at. Power generates heat, and it also generates the potential for a breakdown event, whether it be corona or multipacting. And both of these things are critical. The higher power that we get, the more heat buildup we get, and we have to dissipate that heat. So it is really critical to understand how much power is going to be available. Very often we see requirements of engineers trying to be very conservative as far as what they're rating the power of these individual parts at, and really it ends up driving the design into something that is adding a tremendous amount of cost. And really, when you understand how the part's being used, you have to scratch your head and say, well, gee, why did the engineers specify the power levels that high? Especially when it's operating at 1/10 that value. And we really could have saved significant costs by not redesigning a part, at these very high power levels. On the other hand, there are times when these very high power levels are very real, in which case we have to deal with them, and then that additional cost is something that's just part of fulfilling that need and fulfilling that mission.
So I take it then that electrical specifications are also a consideration.
After all of that, you would think that electrical specifications would be the most important, but it turns out actually that a lot of the packaging requirements, as I just kind of reviewed, in the environments, sometimes are much more important than the electrical parameters. So it's sort of interesting that the first and last parameter that you have to look at are the electrical specs. The first parameter is that it sort of limits some of the technologies that you can use. You then have to take the technologies that are then available, see which of those technologies will operate over the environments and fit in the packaging, and then come back and say, okay, then down select further from there to go back through there and choose your topology that you're looking at. Very often, by the time we get to this stage, we're now looking at compromises for things as far as to actually be able to have the part operate the way that it needs to. Things like packaging size, power handling, bandwidth versus performance is a big one. Like I said, there's a lot of trades to be made in that bandwidth versus electrical performance trade space. For a lot of these components, and it's really important to go through there and understand really how that all comes through and plays. But it's sort of ironic that the electrical performance starts off the discussion and then moves away from the discussion, and then it comes back around to the beginning again, and we have to make sure that we can meet these electrical performance parameters once we've addressed all the mechanics involved in the design.
Wow. After all of that, how do you settle on the best power divider configuration then?
Well, basically what we look for is, and these are sort of generalities as far as to how we start going into this. Lumped element sorts of designs are usually best for low frequency applications, HF through L band. They have a very broad performance and they're rather compact. that can be built for virtually any power level and any mechanical configuration. Once the power level starts to get higher, though, you can no longer have these as surface mount devices. Then we have to go into a larger package. The cooling of these devices at higher power also tends to be through air. So usually you have to have good airflow once you get to higher power, which usually means for very high power levels, there are cooling fans and things like that that need to be implemented. Distributed elements are really the construction of choice for high frequency applications, really UHF through Ka band. They're based on quarter wave transformers and high pass sort of and band pass filters. Therefore, they tend to be band specific, but they can perform very well and have a good robust sort of applications. These can be built in either surface mount or connectorized packaging. A lot of variability here as far as to how we can build these. Getting heat out of a distributed element component is usually conducted through a surface to surface or a conducted heat, as opposed to the lumped element, which is more convection. And this way here we can control the thermals on the distributed elements probably a little more accurately than what we do on the lumped elements. I think the bottom bullet there is talking about packaging, and in essence, with certain caveats, you can take almost any technology and package it into any sort of general class. Clearly there are limits, but then again, trade-offs have to be made to make sure that we tick all the boxes, make sure that we can have the electrical specifications operate over the band that it needs, as well as having work over the required environments.
Okay, could you give us a specific example?
Sure. So this example here is a single sort of hypothetical example. Very often we see S-band sort of applications for antenna diversity. We see these sorts of applications quite a bit for either missile systems or CubeSats. And these are kind of typical power levels where we have a frequency band of 2.2 to 2.4 gigahertz operating somewhere around 20 watts. If this was a ground-based sheltered sort of environment where it is a not really very dynamic environment, a standard DMS 206 SMA would work quite nicely. If this environment was going on a spacecraft, we would start with a DMS 206. What we then do is we would then have to go in there and do some design modifications for multi-pactor. We would also have to go in there and modify the design so that the material selection meets the NASA outgassing requirements. And then as part of all that, we would then have to go in there and design the mechanics of this for interlocking dielectrics, have to transition from a microstrip design to a strip line design to make sure that we don't have a corona breakdown problem, and then check in and make sure that all the materials meet the outgassing requirements. Also for spacecraft operations, usually there's additional data that needs to be taken, whether it's data over temperature or other environmental screenings. Those would have to be included as well. If this was a product that was going on some sort of an airborne application, then there's probably something in between here that we would need to consider. Very often those sort of applications do need to be environmentally sealed, so we probably have to epoxy seal a DMS 206. Very often most of the other parameters are okay the way they are for those sorts of environments. Probably won't have to worry about the interlocking dielectrics if it's just going on an airplane, because the altitude isn't high enough to have those problems go ahead and start to present themselves. So a whole variety of things here for something that's a very simple, very seemingly simple application. Something that a lot of people would just kind of think about, well, let's just put a power divider on and be fine. A lot of considerations that need to be done depending on exactly where it's going.
Wow, lots of good information as always. How about summarizing, Shaun?
Sure. So, at a high level, first of all, we need to know the requirements. We need to know really exactly what does the system need to do electrically, how you're going to mount it, what the environment's going to be in. You have to prioritize that requirements list, because very often you end up with a compromise. You need to have this sort of power level, that frequency, and this much insertion loss. And ideally, of course, everybody wants a perfect component that's going to violate the laws of physics. So we have to go through there, make that list, and then really prioritize it to understand, okay, what is the most important. Very often it's packaging, as far as it has to fit in the box. If it doesn't fit in the box, the customer's not going to be very happy about it. So once that's done, perform a trade study and really determine is kind of the best approach. And then take a step back and say, okay, is this the best solution for the system? This is something that TRM likes to do. We like to go through this list with you, and we will offer what the best example is. Also, by having you share with us how you're going to use this in the system, very often we can take a much more holistic approach to this and say, well, have you thought about this, or have you thought about that, and actually work as a team to come up with the total best solution for the system, which may or may not be the initial power divider that you had thought that you needed. So this is something that we really like to do. It's important because it impacts the overall performance of the system and the end user. And we know for most of our customers, the end user is somebody that if the system doesn't operate, may not make it home that night. And that's something why it's critical to make sure that that we make the right decision all the way through for the system and for the final end user.
Well, I'm thinking that maybe some of that consulting you're just talking about would lead us to the differentiators that TRM brings to the table. You had mentioned that a little earlier. Maybe you could add a little bit more to that.
Absolutely. So one of the big differentiators that TRM has is we like to partner with our customers. We are if somebody would like to have a simple device, want to order something, happy to take the order. But really, where TRM shines is we are a service provider, and we like to go in there and make sure that the component that you need is best going to meet your customer's needs, to make sure that you have the right design and the best design for that particular application. We go through and make sure that all of the materials are selected to meet the final requirements. We use robust mechanical packaging to make sure that the part will survive the environment. And we supply all the objective evidence that the program requires to make sure that we guarantee that our part will function in the system as intended. TRM is a solution provider that also builds hardware. And I think that's kind of the message that we want to make sure that goes out there. And our consulting and discussing these requirements over for you is available free of charge. And it's something that we just like to do to make sure that our customer gets the component that they need for the product that they're building for their end customer.
Well, thank you so much, Shaun. And we do have a couple of questions. I think we have time for at least one. The first one is that this was all about power dividers today. Do you go through similar evaluations when building other components like hybrids or couplers?
Absolutely. This is really sort of a generic sort of approach that we take here at TRM. What we always like to find out from our customers is what it is that they're doing, and then go through these trades. These trades are absolutely critical, whether or not you're dealing with a power divider, whether you're building a directional coupler, or a beamformer, or any other product that TRM manufactures. These sorts of trades are always done, and it's critical that we make sure that we get the right component in your hands so you can do the best job for your customer.
Well, excellent. And any other questions we will answer through email. Thank you again, Shaun, and thank all of you for joining us today. If you are a customer with additional questions, If you'd like to discuss the details of with one of our engineers of one of your programs, we'd love to hear from you. Please feel free to call the engineering hotline. The number's on your screen. There are no costs for these calls. And if you're one of our field sales representatives, then you know your calls are also welcome. And you can also submit questions directly through the sales rep portal. In case it's helpful, our next Tech Talk, it will be on Tuesday, May 17th at 1 p.m. Eastern, and the topic will be testing and verification. Thank you again, Shaun, and thank all of you.
Yeah, thank you, Paul.